Okay, then let's introduce the next speaker. It's an international conference, so we have also to have participants from abroad, and the next speaker is from the USA. He's from the University of Kentucky, Lexington. The talk is on a very topical issue nowadays because we want to convert coal, biomass and natural gas to new diesel, for example. And so it's on Fischer-Tropsch synthesis and it's on isotopic tracer studies. The talk will be given by Professor Davis. So Professor Davis, the floor is yours.
Thank you. I'm glad to be here. This is the first visit. Tracer studies and Fischer-Tropsch synthesis go back to the 1950s when carbon-14 became available. Emmett in the U.S. and Rajetsky in Russia used the carbon-14. When I started on this, I wanted to use carbon-14 because we thought deuterium would exchange too rapidly. The thing I'm going to try to describe is whether Anderson-Schultz-Flory distribution is fact or fiction, whether you have 1 or 2 alpha or more. The deuterium isotope switch is similar to Sitka, but it's on a much longer time scale, where we have to wait for a day or longer, and this is on the order of microseconds. What we're going to do is to come to steady state, let's say in syngas with hydrogen, and then switch to deuterium. And we can do it the other way, where we switch from deuterium to hydrogen. We've done it the same way and gotten similar results. So according to this, we're going to try to identify the accumulation of products and how we can account for this. So we start out doing Fischer-Tropsch with carbon, with hydrogen in this case. After we've gotten stable activity, we then stop the hydrogen, drain all of the collection vessels, and switch to syngas containing deuterium. We then run for roughly a day, analyze the light gases, and then collect the heavier gases and see what impact accumulation has. In order for deuterium tracers to work, we have to be able to have no hydrogen-deuterium exchange. And I knew, and everyone knew for a long time, hydrogen-deuterium would exchange, and so this wouldn't work. That the exchange in the olefin is limited, and that we correct the mass spec data and the GC analysis for the isotope effect. This is to show that there's no hydrogen-deuterium exchange. This is the reactant before and after the mole percent hydrogen exchanging into a deuterated, in this case, octane, but we got similar results with 4 other alkanes up through C18. So that no measurable hydrogen-deuterium exchange occurs under Fischer-Tropsch synthesis conditions. For gas chromatography, this is an example, the deuterated and the non-deuterated, or the deuterated and the non-deuterated, the inverse isotope effect so that the deuterated compound elutes earlier. For octanes, we see that most of the compound is deuterated with very little hydrogen containing. If we go to C10, now it's about equal. We go to hexadecane, the deuterated compound is small compared to the hydrogen. So that there is accumulation of the heavier hydrocarbons, and we have to take this into account. Also in the GC, we have to integrate the whole peak because there is separation of this even if we don't get complete separation of the isotopes, so that we have to integrate the whole peak in order for the GC analysis to be valid. The intensity, we have made mixtures of D0 and D18. This is the GC intensity, measuring the whole peak, and we see it's linear through the whole range. The same thing for hydrogen deuterium, so that we can correct for the different thermal conductivity for the two isotopes. We have run, for example, the octane completely deuterated with hydrogen during the synthesis. We obtain no measurable exchange. When we use the olefin, there is exchange, but only up to about 4 deuteriums if this is hydrogen, or 4 hydrogens if this is deuterium. Pardon me. So that there is exchange, but it's limited primarily to the vinyl positions. The exchange is limited, so if we concentrate on the isomers that are essentially deuterated, then we're okay. So the requirements that we meet, the 3 conditions, we can use deuterium in Fischer-Tropsch synthesis. This is an example of the hydrogen-deuterium ratio that we get when we switch. In this case, we're adding deuterium as D2O, but there is rapid exchange between hydrogen and deuterium. We see this is if we include all isotope-containing hydrocarbons, that the hydrogen-deuterium ratio increases with carbon number. The reason it increases in the first sample we take is because we're measuring products which have accumulated in the liquid phase because they reside in the liquid phase because of boiling point. If we do not include the hydrogen, the D0 is not included, that is, only the hydrogen containing, deuterium containing species are examined, then this is the deuterium containing, and the hydrogen deuterium would remain constant within those products. This means that we have to correct for accumulation of the higher hydrocarbon compounds. And this shows how much accumulation there is by carbon number. For C6, the accumulation is 5% or less. But by the time we get to C18, about 95% of the products that we take one day after switching to deuterium still contains hydrogen. So in order to do a mechanistic interpretation, we're going to have to correct for product accumulation. This shows the situation where we're looking at the alkane over the olefin ratio versus carbon number. This is the data that we get. It fits this equation, 0.3 carbon number exponential. That is a part of the Exxon model in which they assume that the olefin is reincorporating, and that this is why you get the so-called 2-alpha plot in Fischer-Tropsch synthesis. But if we look at the hydrogen-deuterium switching method, now, even then we would get this if we just looked at the products. So that we would get the same that is reported by Exxon workers in their olefin reincorporation model. But if we just look at the deuterated compounds, we now get this as 0.15 in. And since we have some accumulation in the 24 hours, we would reach the conclusion that we are getting essentially a constant amount of deuterated compound form independent of carbon number. So that we are saying that based on this data that the reincorporation of olefins in the higher carbon numbers is minimal in contributing to the 2-alpha distribution. The dark circles are the data that we get based on GC analysis for all hydrocarbons that we collect. But if we just concentrate on the deuterated compounds, the alpha value that we get is 0.9 for the light material, it's 0.9 for the heavier materials. Based on product alone, we are getting different alpha based on the light product and the heavy product. So that the 2-alpha that we're getting here, based on chemical composition at steady state, differs from what we get when we base it on just the deuterated compounds. So that we are saying that up through carbon number 14, we get essentially a single alpha. That the reason that chemically we're getting a 2-alpha plot is because the heavier hydrocarbons are accumulating, and we cannot take that into account simply on a chemical analysis, but for deuterated compounds, we're able then to look at the products that are formed the first day after we switch to the deuterated feed. Pardon me. If I look at the same thing when we use an iron catalyst, the alkane over the olefin, it is not as significant because most of the products up through C16 are olefins. And so the alkane to olefin ratio is much smaller. Chemically, it comes out about 0.2. From the isotope, it's roughly 0.15, but still we reach a similar conclusion as with cobalt, that the primary products come close to being a single alpha. With the cobalt, it's a little less similar, but still much closer than what you get for the 2-alpha plot. So that both cobalt and iron give similar results. We think that it's appropriate to use deuterium as a tracer in Fischer-Tropsch. Apparently, the hydrogen-deuterium exchange is essentially inhibited by the presence of CO. That the alkenes exchange, but it's limited. And so, under our slurry conditions, olefin reincorporation is very limited. It does occur, but it is not sufficient to account for the 2-alpha distribution. And so we would conclude based on this, and we're going to make other runs. If you only do one experiment, then you can explain it easily. If you do several, it sometimes is not as easy. But hopefully the tentative conclusion will hold up for that Fischer-Tropsch follows Anderson-Scholes fluoride based on the products that we get after we switch isotopes, or it's very, very close to Anderson-Scholes fluoride. That diffusion plus reincorporation has a minor impact on product distribution in the small size catalyst particles that we use in the slurry bubble column reactor. If you go to large catalyst pellets, then obviously diffusion has a better chance to impact the results. But in small catalyst particles, diffusion plays a very small part in the reincorporation and is not the reason you get the 2-alpha plot. We believe the 2-alpha plot is because of vapor pressure and accumulation of the heavier products in the liquid that you're using for the slurry reaction. Let me stop with that. And so I say our conclusion is in disagreement, let's say, with the model that Exxon uses for olefin reincorporation to account for the deviation of from the 2-alpha plot. With that, I thank you for the opportunity to make the presentation. Hopefully I'm on time.
The paper is now open for questions. Who would like to start?
Say please. Say please, did you consider it the occurrence of correlation between the HD exchange and the change in the free energy in the reaction? It may be that the exchange occurs in the situations when the change in the free Gibbs energy is near zero, and there is no exchange when this value is big in the magnitude. Did you consider this correlation?
If we run without the carbon monoxide present, then we will get the hydrogen-deuterium exchange. It's not that exchange won't occur. We believe that the alkane in competition with CO does not reabsorb under these low temperature conditions. And so it's a competitive absorption that inhibits the decomposition or the lack of exchange. The olefin does reabsorb to some extent, but exchange apparently is one at a time, and so desorption occurs before we get complete exchange.
Other questions? You mentioned in the beginning something, methodology.
Well, the limitations is that we can't run Fischer-Tropsch and get the products, complete products out in a second or so. So we're stuck with doing a long-term experiment so that this is a slow, older person sifted technique where we take days or a day instead of a second to do the analysis. And that suits me better today than doing it in a second. You just can't. Bell has done this, but he looks at C1 through C4 at most, that the liquid products are where you get the 2-alpha product. And there you have to let the reaction go long enough to accumulate some more products to get out.
So the disadvantage is an advantage.
In this case, so far.
Okay. So,
The people at Exxon, they changed the TLS module. The selectivity went through a maximum. Did you ever try to reproduce these results?
No, we haven't, because you have to make a number of catalyst particle size in order to get through the maximum. And in the slurry phase, I think we're working with small enough particles that diffusion is not going to be a major impact. I think the data that they use is for the pellets rather than for the very small particles. And in order to get to their maximum, I think we would have to use larger particles than what we're using. But no, we haven't. This takes a lot of time to do the analysis. To do it for 5, 10 catalyst particle size would take an awful long time.
Okay. Due to the